Your project does not run on drawings, models, spreadsheets, or software licenses in isolation. It runs on controlled engineering information moving through connected systems, accountable people, and disciplined decisions. That distinction matters because many engineering projects appear productive while their technical information is quietly separating into multiple versions of reality. Process conditions change in one register, equipment data changes in another, model dimensions remain outdated, cable schedules retain deleted loads, instrument tags differ between databases, procurement quantities no longer match engineering quantities, and construction receives documents issued from different design maturity dates. The project may still report progress, but the underlying engineering baseline is already unstable. I want you to look beyond the software names and ask a harder question. Does your engineering environment create one coordinated project reality, or does it merely help each discipline produce its own deliverables faster? Engineering design system selection is not an information technology decision. It is a project execution decision because it determines how requirements, calculations, tags, relationships, revisions, quantities, interfaces, and approvals move from concept development through engineering, procurement, fabrication, construction, commissioning, and final asset handover. When you select and configure the environment correctly, technical information becomes reusable, traceable, and progressively mature. Changes become visible across affected disciplines. Model reviews expose conflicts earlier. Material quantities can be linked to engineering decisions. Construction receives coherent information, and operations receive structured asset data rather than an uncontrolled archive. When you select it poorly, engineers spend increasing amounts of time searching, copying, translating, comparing, and reconciling information. Those hours rarely appear under a single cost heading. They emerge as discipline overruns, review delays, procurement clarifications, supplier queries, site modifications, commissioning punch items, and handover recovery work. The visible cost is software. The hidden cost is engineering friction. The first mistake is selecting tools before understanding the execution strategy. You cannot make a credible selection without first defining how the project will be delivered, where the work will be performed, which contractors will participate, how suppliers will exchange data, when procurement will begin, how construction will package the work, how commissioning systems will be structured, and what the owner expects at handover. A globally distributed project requires common configurations, controlled access, dependable data replication, practical support, and consistent working methods across locations. A brownfield project requires disciplined treatment of incomplete and contradictory legacy information. A modular project requires early control of boundaries, supplier models, transport constraints, and fabrication interfaces. A fast-track project requires design system readiness much earlier because procurement and construction begin before detailed engineering reaches full maturity. Software selection must therefore follow execution logic rather than precede it. The second mistake is believing that a single source of truth means one application must own everything. Complex projects will always use specialized systems, but every controlled data element must have one authoritative owner. Process engineering may own operating conditions. Mechanical engineering may own equipment design attributes. Instrumentation may own device, loop, and termination data. Electrical engineering may own load, feeder, and cable information. The three-dimensional model may own spatial position. Material management may own purchasing and delivery status. Document control may own revision and approval status. The problem is not distributed ownership. The problem is duplicated or undefined ownership. You need a clear data ownership model that identifies who creates each critical attribute, who reviews it, where it resides, which systems consume it, and how changes are propagated. Without that clarity, integration becomes a technical attempt to repair unresolved management decisions. The third mistake is allowing every discipline to optimize locally. Process engineers may prefer one environment, piping designers another, instrumentation teams another, and contractors several more. Each choice may appear efficient within its own boundary, yet the combined project becomes increasingly difficult to coordinate. Local optimization can produce global failure. You need to evaluate every discipline tool inside the wider project information architecture. Ask whether it supports controlled transfer, whether the receiving system understands the transferred data, whether identifiers remain consistent, and whether the project can trace the information back to its technical origin. Manual re-entry must be challenged aggressively. Every time data is copied from a calculation into a spreadsheet, from the spreadsheet into a data sheet, from the data sheet into a drawing, and from the drawing into a procurement register, the project creates another opportunity for omission, unit mismatch, revision error, and interpretation. Entering the same information repeatedly does not create control. It creates multiple opportunities for disagreement. Intelligent diagrams should therefore be treated as data interfaces rather than decorative drawings. When configured correctly, they can connect equipment, lines, valves, instruments, conditions, and system boundaries. They can support registers, consistency checks, downstream transfers, progress assessment, and material takeoffs. However, intelligence does not come from the software label. It comes from configuration, data completeness, controlled symbols, approved rules, and disciplined workflows. A database-backed drawing with missing attributes and inconsistent naming only creates the appearance of control. The same principle applies to three-dimensional design. A model is not valuable because it looks complete. It is valuable because it coordinates equipment, piping, structures, cable containment, access, maintenance clearances, lifting requirements, escape routes, construction interfaces, and spatial reservations. A model can be heavily populated and still be technically immature. Equipment dimensions may remain provisional, valve access may be unacceptable, withdrawal spaces may be missing, cable routes may be incomplete, temporary works may be ignored, and supplier information may not yet be verified. Model percentage is not engineering maturity. Clash detection also requires disciplined interpretation. Automated systems can identify physical interference, but they cannot always determine whether equipment can be maintained, valves can be operated, escape routes remain acceptable, or construction sequences are practical. You still need operability reviews, maintainability reviews, safety reviews, constructability reviews, and commissioning reviews with accountable participants and controlled action closure. A model review without action closure is only a visual meeting. Disciplined databases should drive deliverables wherever practical. Instrumentation environments should support process data, specifications, calculations, wiring, terminations, loop drawings, installation details, control system assignments, cable records, and material quantities from controlled relationships. Electrical environments should support loads, feeders, cables, protection data, single-line diagrams, schematics, and reports from consistent source information. The principle is simple. Information should be entered once, controlled at its source, and reused many times. This is where uncontrolled spreadsheets become dangerous. Spreadsheets are useful for analysis, controlled imports, and reports, but they should not quietly replace official databases. The moment teams begin trusting local spreadsheets more than project systems, the project has created shadow systems and competing technical baselines. Material management must also begin inside engineering. Procurement can manage inquiries, purchase orders, deliveries, and supplier status, but engineering determines what must be purchased. If engineering descriptions, quantities, specifications, and commodity mappings are inconsistent, procurement inherits uncertainty. Your project should distinguish design quantities, requisition quantities, purchase quantities, delivered quantities, installed quantities, and surplus quantities. These values serve different purposes. They must remain traceable rather than being blended into one convenient number. Automatic transfer is useful only when the receiving system understands the maturity, status, and meaning of the data. Document management and data management must also be separated conceptually. Document control manages files, revisions, transmittals, approvals, and distribution. Engineering data management controls tags, attributes, relationships, statuses, and synchronization. You can have excellent document control and still have inconsistent engineering data. Every drawing may carry the correct revision, while the information represented on those drawings conflicts with registers, models, and supplier data. A document should not be issued merely because the file is ready. It should be issued because the underlying engineering information has reached the required maturity. Configuration is therefore part of engineering. Naming conventions, plant breakdown structures, tag formats, units, libraries, templates, symbols, access rights, reports, workflows, and interfaces directly influence technical output. These decisions require participation from discipline leads, project engineering, procurement, document control, construction, commissioning, information management, and the customer. System specialists understand application capabilities. Discipline engineers understand technical requirements. Project managers understand schedule and commercial consequences. Operations personnel understand final handover needs. The configuration must combine these perspectives. You also need staged freezes. Freeze the fundamental structures early, including naming, units, ownership, major interfaces, and breakdown structures. Allow detailed libraries and reports to mature under control, but do not let live production environments change casually after large volumes of information have been created. Every late configuration change can trigger migration, report revisions, interface changes, retraining, and revalidation. Engineering production should not begin simply because licenses have been installed. A system is ready only when it is configured, tested, populated with approved reference data, connected to required interfaces, protected by working backups, and supported by trained users. You should test realistic end-to-end scenarios before scaling. Create an equipment tag, add process data, transfer relevant attributes, create connected instruments, assign electrical loads, place the equipment in the model, generate associated deliverables, extract material information, revise the equipment, and confirm that the change reaches every affected system. If that workflow fails during testing, schedule pressure will not improve it. Pilot projects are therefore essential. Select a representative area containing real multidisciplinary complexity. Do not choose an artificially simple example merely to prove that the platform works. The purpose of the pilot is not to demonstrate success. The purpose is to expose configuration gaps, interface failures, ownership disputes, training weaknesses, and performance problems while correction remains affordable. Training must also be role-based. Users need more than generic software instruction. They need to understand which data they own, which workflows are mandatory, which reports are authoritative, how changes are controlled, and why bypassing the system creates project risk. A designer creating an uncontrolled local library may believe they are saving time. A lead engineer approving an unofficial register may believe they are accelerating progress. A project manager demanding early issue may believe they are protecting the schedule. Each action may create hidden rework elsewhere. The strongest test of any engineering environment is change management. Initial creation is usually straightforward. Revision propagation is where systems and governance are exposed. Consider a pump capacity change. Process conditions may change, equipment data may change, motor power may increase, electrical loads may change, cable sizes may change, foundation loads may change, model dimensions may change, instruments may require resizing, supplier documents may require revision, purchase orders may be affected, and commissioning procedures may need updates. If the project relies on emails and personal memory to manage that chain, change control is not controlled. The same applies to technical queries like deviations and supplier clarifications. Closure should not mean that someone answered the question. Closure should mean that every affected tag, document calculation, model object, requisition, and record has been updated and verified. Commissioning must be considered early. Systems and subsystems should be defined while engineering data is still being developed. Equipment, lines, instruments, cables, and documents should be allocable to commissioning boundaries. When this structure is delayed, commissioning teams are forced to reconstruct thousands of relationships manually under schedule pressure. Handover requirements must also be defined before detailed engineering begins. The project needs to know which tags, attributes, supplier records, document links, classifications, formats, and relationships the owner requires. If these expectations emerge near completion, teams will spend months recovering information that was never structured during execution. A digital handover is not a large file transfer. It is the delivery of trusted, structured, and usable asset information. Fallbacks must be planned because systems, interfaces, and networks will fail. A controlled fallback may involve approved exports, temporary offline packages, standard supplier templates, or interim structured repositories. Every fallback must define who activates it, what work is permitted, how information is captured, who reconciles the changes, and when normal control resumes. An undocumented workaround is not resilience, it is uncontrolled deviation. Engineering managers must own the technical information environment as part of engineering governance. Project managers must fund configuration, testing, training, support, and integration as real schedule activities rather than optional overheads. Lead engineers must define discipline ownership, approve libraries, and prevent unofficial registers from replacing controlled systems. Discipline engineers must record approved technical decisions in the correct place and understand how their data affects downstream work. Progress measurement must also change. Drawing counts alone are not enough. You should measure data completeness, model maturity, interface closure, supplier information status, review completion, action closure, and readiness for procurement, construction, and commissioning. False progress protects reports while exposing projects. The central management principle is clear. Advanced software does not create digital capability. Controlled information does. Your project becomes digitally capable when each critical attribute has an owner, each interface has a defined direction, each change is traceable, each quantity has a basis, each deliverable reflects controlled data, and each lifecycle phase receives information it can trust. That is why engineering design system selection drives project success. It determines whether your project operates as one coordinated technical organization or as several disciplines exchanging documents and hoping the differences are discovered before site work begins. Look closely at your current projects and ask whether your systems reduce rework or merely move it downstream, whether your progress reports reflect maturity or appearance, whether your quantities are traceable or manually defended, and whether your handover will support operations or overwhelm them. Those questions reveal the real condition of your engineering execution environment. For more practical guidance on engineering management, project delivery, design assurance, discipline leadership, automation, and technical governance, follow my LinkedIn newsletter and get in touch with me. Like this episode, share it with project managers, engineering managers, lead engineers, and discipline teams who need to hear it. Subscribe to the channel and leave your experiences in the comments. Tell me where engineering systems have protected your projects, where they have failed, and which management controls made the greatest difference.